Hi, remember we're talking about the concept of path dependence. In this lecture, I want to focus on a very closely related topic or concept known as increasing returns. Increasing returns works as follows. It basically says the more I have of something or the more people that do something, the more that I want of it or the more other people are going to do it. So for example, the more people that get QWERTY typewriters, then the more other people are going to want to get QWERTY typewriters. And there's two reasons for this. One is you can then type on somebody else's machine if they have the same layout. And then also from a production standpoint, if I'm producing QWERTY typewriters, then it makes more sense to produce other QWERTY typewriters. It's going to be costly to rearrange the keys on the computer. So there's these positive feedbacks. More produces more. Now, this idea that more produces more actually exists within the POYA process, right? The more blue balls I pick, then the more likely I am to get a blue ball in the future. And so that leads a lot of people to think, well, maybe it's increasing returns that causes path dependence. And in fact, there's books that are called Path Dependence Increasing Returns. Now, they're not necessarily equating the two, but they're at least putting them in the same box, saying that these are related concepts. And they are related concepts because both the sway of the path process and the POYA process had increasing returns. And the balancing process, which did not produce path dependence, didn't have increasing returns. In fact, it had the opposite. It had decreasing returns. The more red balls I picked, the more blue balls I picked in the urn. So there's clearly a relationship between the two. What we'd like to do is understand, is it logically the same thing? Is increasing returns the same thing as path dependence, or is it something separate? Well, let's go back and look at our POYA process. We've got one blue ball and one red ball. We select a ball and then we return it, and we add a ball of another color. This clearly has increasing returns because if I pick 3 red balls, now I've got 4 red balls in the urn and only 1 blue, and the odds of picking a red ball is going to be 4/5, whereas initially 1/2. So the more red balls I pick, the more likely I am to pick red balls in the future. So there's clearly increasing returns in this setting. But what we want to ask is, does that mean that increasing returns is the same thing as path dependence? Are they logically the same thing? Now here's what's really useful to have a model. And what we're going to do is we're just going to use our urn model, and we're going to see that in fact they're not the same thing. So here's something I call the gas-electric model. And what this is meant to represent is the choice between gas cars and electric cars. Now both of these had positive feedbacks. So when automobiles were first being developed, the more gas cars that were going to be built, the cheaper it would be for other people to build gas cars because all the engines would be being built, in factories. There'd be all these, subsidiary industries debating, creating things like, pistons and stuff like that and fuel injectors. And so gas would beget more gas. And also would create gas stations and that sort of thing in the whole oil industry. And electric would also promote electrics. There'd be electric filling stations and that sort of stuff. So both had increasing returns. But the fact is that at the turn of the century when automobiles were being developed, gas had much larger increasing returns than did electric. So here's how we can represent that. We're going to start out with 5 blue, and blue is going to represent gas, and we're going to start out with 1 red. Now let's suppose that a company rises up that's an electric car company. Well, what that's going to do is that's going to add another red car, another red ball in the urn, because it's going to make electric cars more likely, but it's also going to add 1 blue. Why? Because you could just stick a gas engine on the electric car, and just like you could stick an electric engine on a gas car. So we're going to assume it adds 1 blue and 1 red. Well, what happens? Initially, I've got a 1/5 chance of getting a red ball. After I pick a red ball, I've got, since I've added 1 red and 1 blue, what I'm going to get is I'm going to have a 2/7 chance. So the probability of picking a red ball has gone up. But I'm going to assume that the increasing returns to blue balls are much larger. So if I pick a blue ball, then what I'm going to add is 10 blue balls. Well, clearly, if I pick a blue ball, then I'm going to have increasing returns in blue balls. So what I've got here is I've got increasing returns in red and increasing returns in blue. But if you run this process, what you get is every single time you're going to get the blue balls winning out. You're going to end up getting that blue balls are more likely than red balls. And so this process isn't path dependent, but it has increasing returns. It's just that the increasing returns are much larger for the blue balls than they are from the red balls. So if you rerun history 1,000 times, we'd get gas cars every time. And the main reason is you couldn't carry electricity in a tank. There's no way to just carry electricity around from one place to the next. You couldn't store it, and that storability meant that gas cars had much larger increasing returns, which is why they won out. So increasing returns themselves don't give path dependence. You could have increasing returns and not get path dependence. Then we can ask the other question, which is, could you get path dependence without increasing returns? And the answer to that is also yes. So here's an example. This is an example of symbiosis. So we've got a bunch of symbiotes. Now I've got 4 color balls. I've got blue, red, green, and yellow. I'm going to select a ball and return it. But here's the idea. If I pick a red ball, I'm going to add a green. If I pick a green ball, I'll add a red. If I pick a blue ball, I'll add a yellow. If a yellow ball, I'll add a blue. Well, there's no increasing returns here. So if I pick a red ball, I'm actually increasing the odds of green. But if I pick a blue ball, I increase the odds of yellow. The same goes for green and yellow. So there's no increasing returns. I'm actually helping another type. But if I call this, the red and green balls R star for the larger set of red balls, and I call this blue star, you can see that this is in fact just the Polya process renamed. If I pick a ball from this set, a red or green, I add another ball from that set. And if I pick a ball from the blue-yellow set, then I add another ball to the blue-yellow set. So this is going to be path dependent, but it doesn't have increasing returns. So what we see from the gas-electric process is that you could have increasing returns, but not get path dependence. And what we see from the symbiote process is that we can have path dependence and not have increasing returns. So does this mean that increasing returns doesn't matter? No, but it means that increasing returns is logically distinct from path dependence. So yes, it may be the case that a lot of things we see out there in history in which we have path dependence are the result of increasing returns, but logically they're completely separate concepts. Increasing returns can give path dependence, but it doesn't have to. Path dependence can occur with increasing returns. It can occur without it. Now the EARN models are really interesting, and they've really helped us clarify a lot of stuff, but I don't want you to think that they're the only way you can get path dependence. In fact, in my own opinion, I think most path dependence comes from a very different process. And so I think we're going to just move beyond EARNs and talk about path dependence in the social realm occurring through something entirely different, and that something entirely different is going to be externalities. It's going to be interdependencies between decisions. Remember, an externality is a situation where I make some choice A, and this is just me making this choice. So I choose A and I'm really happy, but when I choose that, if you're over here, this has an effect on you, and maybe it makes you happy, or maybe it makes you sad, but my decision influences you. And these externalities, because of the interdependencies between the choices, can produce externalities. They can do so in really obvious ways. So let me give something that I worked on in my dissertation. My dissertation was written on sort of externalities between large public projects. Now, why large public projects? Because public projects are big. If you think of the economic choices we make, me buying a loaf of bread is a little decision. Somebody building a nuclear power plant, somebody creating a giant national park, creating an interstate highway system. These are huge economic decisions, and they bump into a whole bunch of other stuff. And because they bump into a whole bunch of other stuff, they create externalities. And let's see now how those same externalities create path dependence. So here's my model. There's just going to be 5 projects, A, B, C, D, and E. Each one has a value of 10 on their own. This could be 10 million, 10 billion, doesn't matter. There's a positive value of 10 on their own. But each project's also going to create some externalities. So it's going to bump into the other projects. And we'll see how now we can get path dependence. So I'm going to represent these externalities graphically. These things on the diagonal, the A, B, C, D, E, is just the value of the project. This minus 20 tells the size of the externality between project A and project B. And this minus 10 tells the size of the externality between B and C. And this 5 gives the size of the externality between A and C. So let me get rid of all my drawings here. And now let's think about, suppose that I do project A first. I get a value of 10. Now I'm thinking, do I do B? Well, if I do A and B, I'm going to get 10 for A, plus 10 for B, but then minus 20 for A and B, which is going to be worth 0, so I'm not going to do it. Now if I think about doing A and C, I'm going to get 10 for A, plus 10 for C, but then I get plus 5 for AC, which is going to be 25, which is bigger than this 10, so I'm going to do AC. Well, now I've got to ask, do I do A, C, and D? And if I do A, C, and D, I'm going to get 10 for A, plus 10 for C, plus 5 for the externality, plus 10 for D, but then minus 10 for the externality between A and D. And that's going to mean that maybe I do it, maybe I don't, because I'm sort of indifferent between doing A and D. So you can see if I start with A, I'm not going to do B, I'm going to do C. Maybe I do D, maybe I don't. Well, let's suppose that for some reason I start out by doing B first. And if I do B first, then I'm going to get a payoff of 10. And for the reasons I talked about before, AB is going to be a value of 0, so I'm not going to do AB. But now when I look at B and C, if I do B and C, I get 10 for B, 10 for C, but then the externality between B and C is minus 10. And so I'm not going to get really any larger benefit from doing B and C, so I could decide to do it, I could decide to not do it. Let's suppose I decide not to do it. Well, now let's look at B and D. Now I look at B and D, I get 10 for B, 10 for D, but the externality between B and D is 30, which is positive, right? So now that's value 50, so I'm going to do B and D. So what's interesting here is if I started out doing A, I might end up with A and C. If I start out doing B, I might do B and D. And so there's going to be, depending on not only the initial conditions, but also sort of, you can see as I move down this path, what projects I do in the past are going to affect what projects I do in the future. So these externalities between projects create path dependencies along the way. And it's the positive externalities as well as negative externalities between projects. Now what I did in my dissertation was showing that if most of the externalities were positive, then you actually had less path dependence than if the externalities were negative, because the positive externalities created, again, these sort of increasing returns of public projects and just made it more likely you're going to do more projects, and you didn't get as much contingency as when you had the negative externalities. But the point I want you to take away from this is a big cause of path dependence is externalities, and increasing returns are just one type of externality between decisions. Okay, so let's think about this particular lecture. What have we done? We've said that one thing that people often equate with path dependence is increasing returns. And we've shown that although it may be empirically the case that a lot of path dependence does come from increasing returns, logically they're completely separate. You can have path dependence without increasing returns. You can have increasing returns and not get path dependence. We also talked about how one big cause of path dependence may be externalities, interdependencies between choices, especially big choices like public projects, and those externalities, whether they're positive or negative, can create path dependence, but the negative externalities may have a larger effect. All right, thank you.